I was getting ready for final assembly, but I ran into an electrical problem. The 5-volt reference signal using the Zener diode required too much current to achieve the 5 volts, and I do not want to waste current in a battery-operated system. This was the wire diagram until I discovered this issue. Now to make some changes. The 100 ohm voltage dropping resistor for the contactor is rated at 10 watts, and that's 10 watts of wasted electricity. Also, I discovered that the Zener diode needed 1 amp to regulate at 5 volts, which calculates to 5 watts lost in the diode, 15 watts in the resistor for the diode, along with the 10 watts in the resistor. I decided to use a DC buck converter to reduce the battery voltage down to 20 volts to power the contactor, as well as a simple voltage divider for the 5-volt throttle signal. Originally, I was unable to use a voltage divider because the battery voltage changed too much from full charge to discharge, which would have corrupted the signal. Now that it is regulated at 20 volts makes the voltage divider viable. Here is the new circuit diagram showing the buck converter powering the contactor and my 5-volt reference voltage divider. And here is my spreadsheet I made to easily calculate voltage dividers. I find this much easier than getting out a calculator. There are many variations of voltage dividers on the spreadsheet, but the one we're going to use first is in the lower left. The green cells are for data entry and the yellow cells are the results of calculations. I start with 20 volts at V+, and then look at the amps based on total resistance. We need to make sure there's enough current available to drive the controller. Unfortunately, Curtis did not bother to document the input impedance to the throttle, but tests indicate it is around 100K and needs 0.05 milliamps. Starting with a 25K total resistance tells me I need an 18K and 6.2K resistor, but unfortunately I do not have those values in my resistor kit. Now I will adjust total resistance down until I come up with values that I have on hand. When I got to 12K, it comes up with values I have at 8.2K and 3K. Now moving to the top divider and inserting the standard values shows me what I need to do, and using the 5% resistors gives me 5.35 volts with a total current of 1.79 milliamps, which is only 0.36 watts. Now that the electrical problem is resolved, it is time to reassemble. The 5,000th shim that I had originally installed got torn up. I decided to install a 6,000th shim, but the first thing I needed to do is to get it formed to the shaft, then glue it in place. To preform the shim close to the diameter I need, I wrap it around a small tube, in this case a socket, and wrap it tightly while rolling. You can see it comes out close to the diameter I need. Then I mark it and cut it to length. Here is the actual shim that I will be installing. This time I will be gluing it in place using cyanoacrylate adhesive. But first everything's got to be clean, and I'll do that with acetone. The first rag came off a bit oily, so I did it again with a fresh rag. The inside of the bearing must be oil-free, but I wiped down the shaft just to get the dirt off, and now I'm applying a light coat of oil to inhibit gluing the shim to the shaft. I sat a couple of boards on the rotor because the surface where the bearing would have sat is not a flat surface. Inserting the shim into the bearing and then the bearing shim assembly onto the shaft. Then pushing the shim down until there's just a bit sticking out of the bearing. Zooming in, you can see where I have the shim located. Now to apply the glue, I will carefully lay it down at the lip of the bearing, being careful not to get it on the shaft. The glue will wick down, adhering this shim to the inner race of the bearing. Time to get the main assembly started, and here is my finished transmission bracket. Across the bench I have all my parts and tools laid out. On the ground is the front housing and wheels as well as the rear bulkhead. Here is the battery bracket, miscellaneous hardware, and a few parts. This is my new control panel assembly, the motor, the two bearings, and all the tools. First thing to install is the rear bulkhead, main bearing, and drive shaft. Keep in mind that this is the first full assembly and I anticipate that there will be problems. And the first problem was that I did not have the correct hex bit for the main screws and I had to make a trip to the hardware store. Now that I have the correct tool, we can continue. I did not need that hex bit previously because this is the first time I actually used the lock nut. Now I'm considering how I am going to mate the two halves together. I have the housing down on the ground and I think if I mount it while on the bench it will be too heavy to pick up. I am thinking that putting the assembly on the ground and then dropping the housing on top will be the easiest. First time installing the battery bracket and hoping all the holes will line up. Also hoping that the battery fits.
Woohoo!
I have it tipped over on its side, preparing to install power wiring. Here is the end of the motor speed controller right next to the battery. And here is a look at the back side of the control panel. I have to crimp terminals to the cables, and here are most of the cables already completed, but I have one more to make. Here, clamped in my vise, is a proper cable crimper, and we'll show you how it works. This is my small terminal wire crimper, and it should not be used for cables exceeding 10 gauge. I am using 8 gauge table. If you're careful, it can still be used to strip the ends. A very light squeeze in 2 or 4 places around the diameter and the insulation is cut. Now, as I pull off the end, I will be twisting, keeping all the strands nice and tight. Slide on the terminal and it should be right flush with the end. Pump the handle until the cable is fully compressed, and here is the crimp, but there is a couple of ears on the insulation hanging off. Rotate it 90 degrees, crimp again, and we have a perfect crimp. Now I cut it to length and do it again. Strip, insert terminal, crimp, rotate, crimp, and done. I need to install a resistor for my power light because it is 12 volts but will be connected directly to the battery. This is my method of installing axial leaded components in a wire. You will need a stiff rod about the same diameter as the wire. In this case, I'm using a very small drill bit. Bend the leads of the component 90 degrees. Now, holding the rod parallel to the resistor, coil the lead a few turns around the rod. Trim the end as needed, then repeat for the other lead. The other side is a smaller wire, so I used a smaller drill bit. It was a bit more difficult to do. Now I insert the wire into the formed coils and solder. I do tin the wire first so that the strands are not loose. Using flush cuts, trim off any sharp points, and last, cover with heat shrink. I haven't turned it on yet, but I think I'm done. Here's my new old electric shredder. Now let's go in for a close-up look and tour around. There's my control panel, and we've got a main battery switch, battery status gauge there on the upper right, charging port, Middle switch is a power on, and the right switch is a start. Let's come around here to the other side. And down below we can see our lithium-ion battery, and you'll notice we don't have the power hooked up yet. This will be the Virgin Tri. I have not powered it up yet with it all assembled. Everything else you've seen. We see if we can get a look at the back of the control panel. Don't know if we have enough light in there. You see what's going on with the wiring behind the control panel. And around to the other side, we don't have much light out here. But there's the back side of the control panel. And down here is the main contactor. Now it's time to hook this thing up and see if we flame out. I'm finally ready for the first power up and testing of my new electric shredder. I still have to connect the main power, so I have it tipped over on its backside, making that much easier. First thing I'm going to do is what's called a flash test. This is when you very quickly brush a connector across a terminal. If there's a major short in the system, then there will be a large flash when it sparks. Always a bit nervous when doing this test. I shield my eyes with my hand in case there's a flash. Woohoo! First test completed. Now to repeat the test after turning the main power switch on. In this case, there's a possibility of a small spark if the capacitors in the system need to charge up. Woohoo! Passed the second test, and now I can safely connect the battery. Now with the ammeter connected, I'm going to check to see if the charger is working. Perfect. We have 2 amps charging, which is within the specifications of the charger. During these tests, I have large wire cutters handy, so in case of catastrophic failure, I can cut the battery cables. Wire cutters at the ready. Main switch on. Looking good so far. Now with the battery switch on, here is a look at the battery gauge. Again, wire cutters at the ready on the main battery cable, power switch on, and no failures. Now it is finally time to throw the last switch to start it up, but I'm not going to have my hand anywhere near the system. If it flames out, I will do my best to get those cables cut. 5, 4, 3, 2, 1, fire. Nothing happens. Time to do some troubleshooting to find the problem. I found the problem, and at least I can say it's not my fault. Per the manual for this motor controller, the key switch input that turns it on should work as low as 16 volts. Apparently that is not true because I had it at 20 volts. I had to rewire it so that the key switch input goes to full battery voltage. At this point I already know it will run, but I have not yet ran it up to full power. 3, 2, 1, and now it is finally time to see what it will shred, or if it will shred. I need to move it over next to the pile that has been waiting for 6 months. It's doing exactly what it's supposed to do, but after a few small branches, the chute came loose, so I had to shut down to get it reattached.
Oh no!
Then, after a few more branches, the chute comes loose again. Seems this needs to be resolved. I'm going to change it so that the long screw sticks out both ends, giving the cord that holds the chute something to grab on both sides. I think it is a poor design for attaching the bag, but that's the way it was from the manufacturer. I removed the cover and then cut the head off the screw, making it a threaded stud. Now it looks like it will stay attached. As I sort through the debris, I separated a few larger branches that I will end up running through the chipper. At this point, that side has not been tested. I stopped to go get some shears to trim the branches so that they will feed down the chute. I also have a bucket of old leaf debris to be recycled. A bunch of weeds and lawn debris. I dumped the bucket, but it did not feed well because, as it turns out, there were a couple of large carrots in there plugging the inlet. Now another pause in testing because I wanted to go grab a fresh branch off the neighbor's tree that overgrows my yard. New material. I think it's pretty cool when long branches like that get sucked down and disappear. Now checking the battery display, and what we just shredded used up 10% of the battery power. I'm estimating I'll get at least 30 minutes of shred time with this system. I continued shredding off camera until the bag was full, and now it is time to dump it out and see what we got. The first thing I did, though, was to pull up some weeds that got started under my tree. And now you can see we got some very good mulch that I distributed around the orange tree and then some more around my apple tree. This concludes my project of converting an engine-driven shredder to electric power. If this was the first video you watched, you should go back and look at the other chapters involving the design and building of this shredder. I hope you enjoyed this project, and be sure to subscribe to be notified as I work on other projects around the house. Now, it is time to charge the battery and do some more shredding.